Good morning. I'm Marco Paggi, Professor of Structural Mechanics at MT Lucca and Director of the Research Unit MUSAM on Multiscale Analysis of Materials. I'm also the Delegate of the Director for Research and Technology Transfer, and on his behalf, since he's engaged today in another official commitment, it is my great pleasure to welcome you all to MT Lucca. MT, as you know, is a school of the Italian public system for the higher education, focusing on doctoral studies. In addition, as all the other universities, it is committed to technology transfer. It is therefore a great pleasure for MT Lucca to host this seminar on a topic of high relevance for the paper industry sector, an excellence for Italy and also in the world. This seminar is organized under the patronage of Confindustria Toscana Nord. I would like to thank personally Dr. Claudio Romiti for his support, and with the sponsorship of ASM International. And I would like to thank Marco Celli, Treasurer of the Italy-Switzerland chapter of ASM, and Enrico Borin, President of the Italy-Switzerland chapter of ASM. And they will both deliver a talk and also, let's say, provide the opening address from the side of ASM International in a few seconds. Today we will have three talks. One on metallographic studies of surface treatments and coatings on steels, then another talk on advanced ceramics and coatings, and finally one on metallographic studies for failure analysis. Two of them, as you may note, are delivered by a well-known international researcher, George van der Voort. He graduated from Drexel University and Lehigh University in metallurgy, and he has also 29 years in the steel industry. So he has really he has a lot of experience to share with all of us. He was also past president of the International Metallographic Society and past chairman of the ASTM Committee E4 on metallography. And George was also the USA representative to ISO on metallography for 25 years. And he has more than 400 papers, scientific articles in the field of metallography. So for us, it's really a great pleasure to have him here to share his knowledge on metallographic techniques, and especially related to paper industry. Just to say a few words to introduce the topic of today, let me presentation version here. Just, well, paper making in Lucca has a very long tradition. Already in the middle of the 15th century, there was the first paper mill in Lucca by Vincenzo Busdraghi. This is very well known. And then later on, at the beginning of the 19th century, we had already 100 paper mills. And then later on in 1971, 211 paper mills. And still today, of course, the paper making industry in Lucca is very active and, let's say, I would say powerful, and able to have a very important international impact. And you can see these, for instance, the historical aspects in Museo della Carta and Pesce, for instance. But if you look at the history of paper-making machines, because today we will talk about the, let's say, materials for improving our productions, improving our technology, then the history of paper-making machines has a very long, is also very long. In 2014, when I was in Paris as a visiting professor, I was visiting as a tourist at Musée des Arts et Métiers, and there you can find this very nice picture and also a model in scale, 1:5, of an old paper-making machine at the beginning of the 18th century. Well, as you can see, it's something that maybe the principle is similar to what we have today, but the machine is totally different. And in fact, if you look today in a modern, let's say, modern company, these are two pictures taken from a leaflet by Marco Celli. I would like to thank him for providing them to me. Well, you can clearly see that it's not the same production line as in the past. So there was a huge progress, and something can still be done. Challenges, well, high production speeds, This requires reliability and safety conditions, high temperatures. We need to have optimal thermal properties, and also we have very often fluid-solid interaction. So these are also topics quite interesting and not trivial, so they require research. And also high contact stresses, so contact is present everywhere in our machines, for paper in different stages, but also in the Yankee dryer as well. And this is just a picture there. So you need to have a roughness control. You need to avoid, let's say, well, the non-planar, non-smooth surface, optimal surface properties, so very hard on the layer and so on, and coatings, therefore, so spray coatings or other type of coatings that could be used. And why not also using composite materials? So you see clearly that there is a range of possibilities for modern mechanics and, let's say, material science to make a progress in paper-making machines. Let me say empty Lucca, and then I conclude. I leave the floor to Marco Celli. As a museum lab, is a laboratory with specific facilities also for technology transfer. Of course, for research, this is supported by the European Research Council. We had an ERC starting grant of 1.5 million euro that allowed us to build such a lab. In the lab, we have many nice, let's say, experimental equipment with also some unique feature in Italy. And we can perform failure analysis. This is one of the research topics that can be of interest also to paper industry. Surface characterization with confocal perfilometer. But we can also test, in other examples, we had a collaboration with the local industry here for adhesion between paper tissues. You can clearly see inside the scanning electron microscope, by performing a mechanical test, how cellulose fibers are interacting, and so how also chemical issues are present there. So in principle, we have high potential for collaboration and technology transfer, and we really hope also, thanks to the Giotto, the Joint Technology Transfer Office of MT Lucca, Scuola Normale Superiore di Pisa, and Sant'Anna, to have an impact on the local industry in the future even more. And thank you very much for being here, and I leave the floor to Marco.
Buongiorno a tutti, io vi parlerò in italiano perché il mio inglese non mi permette di fare lunghi discorsi. E quindi mi scuso con quelli di lingua inglese e magari qualcuno gli aiuterà o gli dirà le cose essenziali, io poi non ho da dire molto. Quasi tutti credo qui mi conoscono, però per i giovani dell'istituto qui dell'IMT, io sono un tecnico dell'industria cartaria, oramai un po' grandicello perché sono oltre 50 anni che lavoro in questo campo, soprattutto nel campo del macchinario per l'industria della carta. Qui nella zona di Lucca l'industria della carta è l'industria preponderante e comprende, a rifarsi dai produttori di macchine, anche poi la fabbricazione della carta, in particolare quella da imballaggio e la carta tissue. Manca la carta bianca da scrivere e da stampa, che però una volta magari c'era, perché c'erano anche cartiere che facevano carte pregiate proprio, che sono andate a scomparire. Poi ora con i computer probabilmente è l'unica carta che serve è quella per fare le fotocopie, perché poi tutto si trova sul computer e la carta da scrivere e da stampa serve sempre meno. Invece fra i produttori di macchine e i produttori di carta si è creata una sinergia che ha consentito alla zona di Lucca di raggiungere una posizione preeminente, direi proprio nel mondo, come polo di produzione di carta e di macchine di qualità, e che viene poi ora apprezzato un po' in tutto il mondo, perché le nostre macchine vanno a finire in tutti i paesi, e anche i nostri produttori di carta si sono ampliati e stanno occupando spazi proprio in ambito mondiale. Quindi, sfruttando questa situazione, io vi dirò che sono associato all'associazione ASM da moltissimi anni, tant'è vero ora sono un life member, in quanto è più di 30 anni che ho questa associazione, che partecipo a questa associazione. Ho avuto modo in questo ambito di conoscere tecnici di grande livello e di trarne anche un beneficio nella conoscenza dei materiali e delle tecnologie che poi si possono applicare anche in ambito della costruzione delle macchine per la carta. E quindi è stata una cosa che ritengo molto utile. E in questo senso sollecito un po' tutti a partecipare a questo tipo di associazioni, perché se ne ricava sempre conoscenze e informazioni e che poi durante la vita, durante il corso professionale potranno venire utili. Io in questa occasione la mia funzione è quella di fare un po' da tramite fra i tecnici e direi licenziati del campo dei materiali e della metallografia, come appunto abbiamo qui presente George van der Voort e Arrigo Borin, e il mondo dell'università, che qui appunto dove ci troviamo, e creare poi una sinergia che serva anche all'industria, che possa procedere, magari fare un passo avanti, stare al pari o addirittura, se possibile, avanzare rispetto alla competizione mondiale che oramai tutti quanti dobbiamo affrontare. Quindi credo che la mia funzione qui si esaurisce e lascio la parola ai nostri relatori, che ci sapranno spiegare bene le loro materie. Grazie.
So the first speaker is George van der Voort. He will have a talk on metallographic study of surface treatments and coatings on steel.
Buongiorno. I'm afraid that's the end of my Italian. I can only talk about food and wine. It's just not today's subject. The talk today is about the metallography of surface treatments and coatings, and there's very little emphasis on the surface treatments. I'm just going to show an example of a shallow hardening steel and also an induction hardened steel. All the emphasis is on coatings. And we really don't have enough time in an hour to get into the minutiae regarding how to prepare these specimens properly and etch them properly. If you wish, you can go to my website. Just either punch in George van der Voort into Google and it pops up, or it's www.georgevandervoort.com, no punctuation. And there's things that, on the topic there. We'll start with the two surface examples. This is a water hardening tool steel type W1 in the AISI designation system. In the upper left, and of course this is just a carbon steel, and it's 1.05 weight% carbon nominally. W1 grades cover several different ranges of carbon from 0.7 to 1.35 weight%. The most common grades that are sold are essentially 1 to 1.1% carbon, such as this one. And there's manganese and silicon, but nothing else in them other than some trace elements. And so they're low hardenability, and you either brine quench them or water quench them, and they're not through hardening unless the diameter is very small. And here you can see on the upper left the normal hardened surface, which is all martensite with undissolved carbides, because you don't want to put all 1% carbon in solution when you're heat treating a W1 tool steel, or any tool steel for that matter, that are above 0.5 weight%, because you'll get into problems with grain growth and retained austenite and rapid fractures. Now, if you etch the sample, on the upper left it's etched with nitol, which this is as quenched. On the upper right, because it's as quenched martensite, pickerel will not etch as quenched martensite unless it's been tempered. And you can see that we see the carbides, but we don't see any martensite. On the lower left is the transition zone. When you etch with pickerel, you're darkening the perlite, but not the as quenched martensite. So you have a very strong color contrast, and you can easily assess the approximate location or depth for 50% martensite, 50% perlite. And on the lower right is the core microstructure, and you can see this is fully pearlitic with the undissolved cementite. And the hardness, of course, is lower, only 43 Rockwell C hardness, but that's pretty good for perlite. And you can get rather high hardnesses with fine pearlitic microstructures. But of course, it's not as hard as the as-quenched martensite at 64. Now, here's a series of 3 micrographs of 1045 carbon steel that was induction hardened. In induction hardening, you're only at heat for a few seconds before you quench. And so you have to have a starting microstructure that has a very uniform, fine distribution of carbide, or you're going to have serious problems because you don't have the sample at temperature long enough to diffuse carbon and make the carbon content in the austenite uniform. So you have to have a good starting microstructure for that. On the left-hand corner, you see the surface microstructure, which is 100% martensite. In the center, you see the transition zone from 100% martensite. We're now getting perlite, which is a dark constituent, and some bainite is in there, and but not much proeutectoid ferrite. And on the right-hand side is the core microstructure, which is rather coarse perlite colonies, and there's a ferrite, proeutectoid ferrite in the pyroaustenite grain boundaries. And you can see that's at 500x, but it's a relative, they're all at 500x, but it's a relatively coarse structure. Now, let's get into all the other types of treatments. And the first one we're going to cover are carburized surfaces of steel. This is 8620 alloy steel, and actually these failed in service, but not these teeth right here. These were ones that didn't break. And we have etched this with a reagent developed by Emmanuel Baraha, or as I sometimes say, Baraha haha. Baraha was born in Sofia, Bulgaria, and when World War II broke out, his family moved to Israel, and I probably don't have to tell you why they did that, but he did his all his studies at the Technion in Israel, and developed some very good color etchants. The color etchants can be very useful for seeing composition and phase differences. At the lower part of the picture, is the unaffected core. And you can see the teeth have a much different microstructure, in this case high carbon martensite. Now, we can further look at this. The microstructure, this color etch here, for revealing the case on the left is not the best etchant to use. But the one on the right, it's very good for the core lath martensite. It's not as good as certain other color etchants for the martensitic high carbon surface layer. Those are both at 500x. But the core with the lath martensite comes out beautifully definitive. You can see the different orientations of the lath much better than you can with nitol. You know, most people use nitol for everything. They never try anything different. Now, this was a carburized P5 plastic mold steel. P5 has a bulk carbon content of 0.07%. And so you see on the right-hand side there, the microstructure in the center. Since you're carburizing it, you're going to select the austenitizing temperature based on the carbon content of the case, because you're trying to get the best case properties. And that happens that for the core, that temperature is in the two-phase alpha plus austenite field. And so when you quench the sample, you can't get 100% martensite in the center because you didn't start out with 100% austenite in the center of the part. And you can see the dark constituent on the right-hand picture is the low-carbon martensite, and all the white there is ferrite. And there's if you see that one arrow just to the left of center, that's pointing to some ferrite that precipitated during the quench onto the surface of the pre-existing ferrite from the austenitizing temperature. And you can barely see that here. You can see it because we're looking at it in the Marsky differential interference contrast illumination, which is showing some height differences. But with the color etch, you can see that much better. In the upper left, you see at 100x, the carburized case has a very pronounced layer of cementite in the prior austenite grain boundaries. The proeutectoid cementite is coming out. And that made this part extremely brittle, and it failed as soon as it was put in service. On the lower left, at 1000x, you're seeing some of the grain boundary carbide that's at the end of the zone there in the picture above it. Now, here are some color micrographs using 10% sodium metabisulfite, which is a very good etch for martensitic structures. And we're looking at it with polarized light and sensitive tint. And in the upper left, we're at 50x, and you can see at the top is the carburized surface that has a very high carbide content. On the upper right, it's at 100x. On the lower left, it's at 200x, and you can see that carbide much better. On the lower right, you can see there's actually a film of cementite on the surface. At 500x, you can see that. And that's a very poorly carburized sample. And of course, it failed as soon as it was put in service. Now, here are two examples of different color etchants. On the top is sodium metabisulfite, and you can see where the ferrite versus the martensite nicely. But Clem's number one on the bottom, and we're looking at two different areas, 500x. All the pictures are 500x. But you notice that the initial ferrite that was present during the austenitizing temperature, which would have a higher carbon content than the ferrite that's going to precipitate later during the quench, that first ferrite is blue, dark blue, and then the film of ferrite that is forming during the quench is almost a white color. And Clem shows that beautifully, but nothing else does that. So the color etchants have enormous value in doing work in microscopy. And one of the reasons for this is that the human eye is only sensitive to about 40 different shades from white to black. But our eyes are very sensitive to color differences, differences in hue, saturation, and so forth. And that gives us much greater sensitivity for looking at microstructures in color compared to black and white. And many of the color etchings are phase specific. Now, here is a sample of 8620. It was gear, and this tooth itself didn't break, but others did. And the gear broke very quickly in service. And I've etched this with 10% sodium metabisulfite, and we're again photographed in color, in polarized light and sensitive tint. And those circles are surrounding regions of very high carbide content, and particularly intergranular carbide. And at the top surface, the yellow arrows on the left, right surface and the top are pointing to a layer that was decarburized. So after they carburized the steel, and you can see the carbide, the excessive carbide is not uniformly distributed. It's erratically distributed. But after they carburized it, when they heat treated it, they decarburized the surface. And at higher magnification, you'll see that the areas with the arrows pointing to it have perlite and ferrite patches there. And of course, that's not going to perform well in service. That picture's at 200x. Now here we're at 500x. And we're looking at it with different techniques. The one on the right is the Marsky differential interference contrast. And, but it's the same etch. And you can see all the white in the arrows are pointing to in the matrix on the left. That's the grain boundary cementite and near the surface. But, and at the top, the white arrows are pointing to a layer which has ferrite, excuse me, it's mostly perlite, but some patches of ferrite. And you can see a couple more patches of ferrite in the right-hand picture. But the matrix is plate martensite, which is rather coarse, and retained austenite. The irregular shaped patches of white on the left-hand picture, which is in bright field, is all retained austenite. And you can always tell the carbide from the retained austenite because the carbide particles are long and smoother, whereas the retained austenite are small and they're angular particles, or angular-looking phases. Now here's another shot of the one of these patches of excessive cementite. And again, this is 10% sodium metabisulfite, and we're photographing it in the Marsky DIC. So the yellow arrows are pointing to these patches of proeutectoid cementite. And you only need to cover about 60% of the grain boundary surface area per unit volume before cementite will make the steel as brittle as glass. And you don't have to have 100% of the grain boundaries covered to have that problem. But this is a nice example of how not to carburize a sample. And here's a same gear, two different teeth, and I've etched this with alkaline sodium picrate near the boiling point, which would be 100 degrees C. I keep it below the boiling point, generally around 90 degrees C, because if it boils, the composition can change as you're etching. And it gives off more vapor that you can breathe in, and there's no reason to do that. And so it was etched for 90 seconds. But you can see now all the excessive cementite, which is very irregularly distributed, which is extremely unusual. I've never seen another carburized sample with such an irregular distribution of carbides and as this. And it's really odd. But also it failed. Now, here's some new hardness readings taken on this at 100-gram load on this sample that was carburized. And you can see the case depth is a bit irregular, up to about 3/4 of a millimeter, or maybe 8.8 millimeters. And then the hardness goes up again because there's less of the carbide in that area and less retained austenite. And then it starts dropping down to the core hardness. Now, this is what the case and core look like if we etched it with nitrile. And you can see that the results are nothing exciting in comparison to using color. And here's a different etch for this sample. Oh, wait, I'm sorry. This is a different specimen than the previous one that I'm showing you. This is 8620 that was carburized, and then it was deliberately heat treated to form low carbon martensite at the surface and tempered lath martensite in the core. And this is what the structure looks like at the surface on the left and the core on the right. So on the left is lower bainite, on the right is lath martensite with nitrile. Now, here's the heat treatment. It was carburized at 1750F, then quenched into a 50-50 mix of sodium nitrate and potassium nitrate at 480 degrees Fahrenheit, held for 2 hours, and then it was air-cooled and then tempered at 480 Fahrenheit for 4 hours. And the hardness was 614 Vickers, or roughly 56 Rockwell C hardness in the case. And we're etching it with 10% sodium metabisulfite. And here you can see that in bright field, you really can see the lath martensite beautifully. And polarized light and sensitive tint didn't really help us see the structure better. Sometimes if your coloring is a little weak in bright field, if you go to polarized light and sensitive tint, it can be remarkably better. In this case, the bright field was excellent. Now here is the core microstructure. And the core has a hardness of 421 Vickers, which is about 42.5 Rockwell C. And we're etching again with 10% sodium metabisulfite. And now on the left in bright field is the lath martensite of the core. But when you go to polarized light and sensitive tint, the core microstructure is much, much better revealed. So it's interesting that the case microstructure, the lower bainite, was better revealed just in bright field, and the core with lath martensite was much better revealed when we went to polarized light and sensitive tint. But you can see those kind of things when you're doing work in color. But those microstructures are far better than what we see with nitrile. Now, this is a different color etch. This is one of Baraha's sulfamic acid reagents. It's the number one in the original paper he published, which is 100 milliliters of water, 3 grams potassium metabisulfite, and 1 gram sulfamic acid. And the sulfamic acid etchants really work beautifully. And we're looking at both of these in polarized light and sensitive tint. On the left is the case, on the right is the core. So on the left is lower bainite, on the right is lath martensite. And here's the hardness profile, again using 100 gram Knoop read indents. The Knoop indenter is very good for showing hardness differences as a function of distance or depth from the surface, whereas the Vickers indent, because of its square shape, is much more difficult to use for this purpose. And you can see that the lath martensite is up around 600 Knoop, and then the core is a bit over 400. Now, I want to show you some examples of 87. It's not technically 8720. These are gears for railroads, bearings, and they were made by Timken, and it's a proprietary grade, but the composition is close to AISI 8720. So what we're seeing here now is a specimen that was tested with X-ray diffraction, and they found 25.4% retained austenite using X-ray diffraction. Now, the problem when you're trying to look at retained austenite with the light optical microscope is that you cannot see any retained austenite until you get at least 10 to 15% by volume. Once you have at least 10 to 15% by volume according to X-ray diffraction, you can start to see it. But when you have low amounts, you're always going to have this problem. I'll show you examples where we have like 60, 70, 80% retained austenite. Then there's no difficulty seeing it. But this is X-ray diffraction. Now, on the left, the sample's been etched with 2% nitol. On the right, it was etched with 6% nitol with a wetting agent called zephyrin chloride, which is often used with pickerel to try and improve the etch results. There was a paper published many years ago in Nature. A man took 5200 bearing steel and he austenitized it at the correct temperature, and then he kept going up higher and higher in temperature. And he claimed that he could visually see 2% retained austenite in a steel. And I've never seen anybody who could ever do that. And he claimed that by adding zephyrin chloride to nitol, he was able to do that. And the X-ray diffraction results said there was 3%, but visually he claimed he could measure 2%. I don't know of any human being who's ever been able to do that other than this guy's claim. And I don't believe his claim at all. But you can see here that we're nowhere near 25.4% retained austenite. And by image analysis, we got, I think it says 13.3%. I can't see the text too well from here. But that's far below 25.4%. Now, here we're using the Meyer-Eckholt #2 reagent on the left and 10% sodium metabisulfite on the right. And you can see that we got 10% with sodium metabisulfite and only 6.2% with Meyer-Eckholt and austenite. And then with sodium metabisulfite, we got 7.1%. And so those results are nothing fantastic compared to the X-ray diffraction results. And I've seen this problem over and over. And in my career, at least 3 times, I've heat-treated specimens at different austenitizing temperatures where they have like 1% carbon in them or more, and gone through this experiment. And I've never been able to do it. Now, this sample, X-ray diffraction said, had 19.7% retained austenite. And on the left is nitol, 2%. On the right is 6% nitol with 1% zephyrin chloride. And we're getting markedly lower results, only around 8.5%. So you can see in both cases the amount we can see and measure by image analysis is at least 10% lower than what X-ray diffraction said. And here it's etched with the other 2 samples. The picture on the right, the surface was coated with Electro nickel. That's what that white layer is. But that, of course, was not there when they did the X-ray diffraction work, only afterwards. And you can see the 10% sodium metabisulfite, we got 5.7%, and Meyer-Eckholt gave us 6% by image analysis. So we're at least 12% lower. And this is a very common problem. Now, this one was 16.2% retained austenite by X-ray diffraction, and 2% nitol on the left. You don't see any retained austenite there, and 6% nitol with 1% zephyrin chloride on the right. And we managed to pick up by image analysis 1.2%. So about 15% we couldn't detect at all. And that's pretty normal. And here with the Meyer-Eckholts on the left, 10% sodium metabisulfite. Again, Meyer-Eckholts with image analysis, we got 0.8% retained austenite. And then the 10% sodium metabisulfite, we got 1.1%. So in all 4 etchings, we're way below the X-ray diffraction results, by close to 15%. Now let's look at some nitrided surfaces. This nitriding is an area where you can find a lot of bad literature, particularly in talking about the compound layer and also white etching phases in grain boundaries that are essentially parallel to the nitrided surface. This is a microstructure of a failed chuck jaw that was made for a lathe. And it was made out of tool steel Bethlehem had called luster die, which is 41S50 actually, or 41B50, excuse me. And it was gas nitrided, but had a very thick, brittle white layer of iron nitride that initiated cracking. In the upper left, that first top layer is electrolysis nickel, and then below that is a dark black area of some oxide that formed on the samples, and then below that is the compound layer, and that's only 50x. But we're etching with the sulfamic acid reagent, and you can very clearly see the change in microstructure from the nitrided surface to the non-nitrided surface because of the color difference. It's very clear, and you can see the arrow pointing along the left-hand edge of the picture to the maximum affected depth. On the middle, it's etched with nitol, and we're at 200x, so you can't see the whole case. But you can see that brittle white layer. There's no electrolysis nickel on that sample. But the surface in that compound layer exhibits different color, a gray near the surface and pure white below it. And then below the compound layer, you can see white etching, a white etching constituent in the grain boundaries. And there are many articles published where people claim this is iron nitride. It is not iron nitride. And on the right is Barajas cadmium sulfide reagent. And again, you can see the maximum affected case depth very, very well with that. Now, here are two examples at higher magnification. Then you can see the compound layer underneath the nickel coating and that oxide layer on both pictures. There are different magnifications. 50x on the left and 200x on the right. And these are both etched with Barajas cadmium sulfide color etch, which is a very good color etch for cast irons and steels and all kinds of steels. So the yellow arrows on the right, the two, not the one at the top, well, even the one at the top, they're pointing to these white layers in grain boundary or grain edges that are almost parallel to the top surface. And in the literature, people all claim that this is iron nitride. Now, here's a sample, the same material but repolished, and we're etching it with sodium metabisulfite. I don't have the etch listed there, but it is sodium. This is sodium metabisulfite. The red arrows are pointing to manganese sulfide inclusions in this steel. It's lightly resulfurized in that they're adding, the limit for sulfur in this grade is 0.045 weight percent. And to improve machinability, they're working to a sulfur level around 0.03, which is a legal low normal amount of sulfur, but it gives a little better machinability. So those are the manganese sulfides, and that's the original longitudinal orientation of the sample. And you can see the electrolysis nickel plating at the surface, and then there's this oxide layer there of some kind of scale. And then you see coloring done by the alkaline sodium picrate. Can you turn that down? Nobody's going to be able to see the images. This is at 500x. You need a good. Better. Okay. Doesn't have to be completely off. Now, here's some additional micrographs of this sample, the 41B50 chuck jaw, and we're etched with 10% sodium metabisulfite here, and looking at it with polarized light plus sensitive tint. And in the upper left, you see at 50x, the case area with the electrolysis nickel coating on there, and then the oxide layer, and then the light etching compound layer. On the upper right, it's at 500x, and you can see cracks in the black portion or dark portion of the compound layer. And the electrous nickel plating is just barely visible. And to the left of where it says the magnification bar and 20 micron is, you can see a grain boundary loaded with a second phase, which is not being colored by this etch. On the lower left, you see the transition zone from the hardened surface to the non-hardened surface, or at least lower hardened surface, because it's not affected by the nitriding process. And you can clearly see that zone. And then the lower right is the core microstructure, which is a 50 carbon tempered martensite in this case. And it's totally non-nitrided. Now, here's a higher mag view of that surface that you saw in the picture there. Just the picture is enlarged on the screen here. And you can see the cracking with the blue arrow pointing to the cracking in the dark part of that layer. And this is just using 10% sodium metabisulfite now, nothing else. And there's precipitates in the lighter part of the nitrided compound layer. And the red arrows are pointing to the grain boundary white etching film, which has been claimed repeatedly in the literature to be iron nitride. And here's another view of the same thing, 500x. Okay, now we're going to etch this with alkaline sodium picrate at 90 degrees C for 90 seconds. And that etchant colors cementite. Nothing colors iron nitride. And you can see the electrous nickel plating at the top is unaffected. Then we got the black line, which is some kind of oxidation product. And then you can see the compound layer now has a lot of etching. That original dark area is still dark, but below that, and on the right, you can see it better. We're at much higher magnification. You can see blue constituents, and that's cementite. And then down below in the matrix, you can see the manganese sulfide particles. They're dark, but the grain boundary surface film now is colored dark, like a blackish. And that means it's cementite, not iron nitride, because you cannot color iron nitride with any technique, any etchant at all. But alkaline sodium picrate colors cementite. That's its main purpose in use. Here's another example of the coating at the surface, but at a little higher magnification than before. And you can see the red arrow that's pointing to the compound layer. All that blue is cementite. And the red arrow that's pointing to the dark region in the grain boundary, that's cementite. And the manganese sulfide is still present. And on the right-hand side, the red arrows are pointing to those grain boundary films that were white with nitol and other etchants. But alkaline sodium picrate darkens it, proving that it's cementite, not iron nitride. Now, if you read in the literature, you'll see that many years ago, a lot of people like to etch nitrided surfaces with a 10-to-1 solution of 4% picrel and 2% nitol. And just for the heck of it, I etched these samples with that solution. I have not seen anybody use that etch in many, many years. But it was widely used in the earlier days of developing nitriding processes. But for some reason, it's become unpopular, or people just don't read the literature. And you can see that on the right-hand side and the left-hand side, that it is etching the compound layer. And it does a nice job there. So, you know, we have the three zones that we saw before. One is that oxide layer on the top surface, and then, or there is the oxide layer on the top surface, and then there's a compound, a little bit of a compound layer there, very thin, and then the dark etching area, which seems to be different than the rest of the nitrided compound layer, which is number 3. One of these days, I'm going to try and do EBSD on the sample and see if I can shed more light on the composition variations in there. But I haven't had an opportunity to do that. And here's a manual new hardness traverse on this specimen. And you can see the thickness of the white layer there is quite small. The maximum depth of the cementite grain boundary films is a little less than half a millimeter. And the visual estimate that I initially made of the maximum effective case depth, you can see is somewhere near maybe 0.8 millimeters. And the hardness is a little bit under 500 Nup. And here's an example of some of the Nup traverses with Nup readings. The outer part of the compound layer, you can see a very large indent there. And then the next one that's closest to the surface is pretty big, and then below that it gets much smaller. So there's something very unusual going on with the composition of that compound layer. But if you look in the literature, you won't find anybody who's really studied the true microstructure and composition and phases present in these white etching compound layers. And these layers invariably cause failures. I can show you samples of, I have a lot more micrographs on nitride as samples. I can show you samples where the steel, after nitriding, performed perfectly and there was no compound layer. But the same steel where they had a compound layer had very, very poor service life. So this is well known. And here's the hardness of that chuck jaw. And you can see at the extreme surface, it's very low hardness, only about 350. And in less than 1 millimeter, jumps up to 800 and then drops down, reaching somewhere around 0.8 or about 8 millimeters, the core hardness. Now let's look at some borated surfaces. This is a German alloy steel, 42CR-MO4, which is similar to our 4140 alloy steel in the ASI system. And this was an as-rolled sample that was borated. And on the right-hand side, we're looking at 1000X. And you can see we have very good edge retention. The borated surface is rather brittle. If you drop a Vickers indent in there, you'll have cracks coming from the corners. On the left in the microstructure, you see that we have a lot of, the one arrow for perlite moved on me. That should be pointing down to that patch. The dark patches are perlite. The matrix is bainite. And my arrow somehow moved in working on it. And also, you can see the magnification indexes, 50 micron on the left and 10 micron on the right, are way above the mag markers. Somehow they moved and I didn't notice it. But that's the as-rolled structure. And I also have a similar sample that was tempered martensite and looks identical. The borating is, surfaces are often used when the part is wearing against glass. It seems to be a very good coating for wear against glass. Let's look at some nickel boron coated samples. This is a carbon sheet steel coated with nickel boron and etched with nitol. You can see the grain structure of the sheet steel is not very equiaxed and is somewhat elongated. And there's cracks in the nickel boron coating. And here it is in color. And this is Clem's #1 reagent. And on the right-hand side, we're at a higher magnification, which is 500x. 200 on the left, 500 on the right. And you can see the structure within the nickel boron coating very nicely. And the interface is quite clear, and the good edge retention. Let's look at some additional coated surfaces. Now, these are hot dip coatings, We can have zinc, either galvanized or galvannealed, Galvalume, which is zinc aluminum. We can have aluminized surfaces. We can have electro-galvanized zinc, which is done electrolytically, and also a zinc nickel electro-galvanized. And here is electro-galvanized sheet steel, etched with 1% nitric acid and amyl alcohol, which stinks to the high heavens, but it's very commonly used for this purpose. And you can see we have no compound layer at the interface. The top surface is single-phase zinc, and this, when you do the electrolytic deposition of zinc on steel, it only reduces the fatigue endurance limit by 7%. When you hot dip galvanize, you're reducing the fatigue endurance limit by 40%. And that's because we get compound layer. And here's an example of galvanized sheet steel. And you can see along the interface, we've got a second phase. And this is an etch that was developed by Jimmy Kilpatrick at Homer Research Lab for the galvanized steel. It was published around 1990 in Praktische Metallography, or Practical Metallography, the German-English publication. And if anybody's interested in the composition, I can give it to them. But that's going to perform more poorly in fatigue applications than electrolytic. But it's, of course, hot dip galvanizing is much easier to do, much less expensive. Now, these are 3 different samples of galvannealed sheet steel. And they're etched with the same reagent. And you can see in the upper left, we have gamma phase along the surface at the interface, which is FeZN4. And it's brown when you look at it in a microscope, but these are black and white pictures. And delta phase is FeZN7, which is light blue or blue-brown in an actual color. And there can be 2 different forms of that. And on the right, you can see we have some zeta phase along the top surface. That's FeZN13. That's either blue or bronze, but it's always at the surface compared to the others. And the bottom picture, we've got some free zinc, very small particles in there. And these were done by, pictures were done by Robert Nestor at Homer Research Lab, a colleague of mine when I was there. And here's another example with this same kind of constituents as before. Now, this is Galvalume sheet steel, which I had prepared. And this, on the left is this typical vertical mount where the plane of polish is perpendicular to the sample. On the right, we're using a taper mount. Struers sells a fixture where you can put your sheet sample in there and you have a known angle, and then you mold it. You make like a epoxy mount, and now you're polishing with the sample at an angle to the surface. So you're getting a magnification in the vertical direction on the sample, but nothing in the horizontal. And on the left, I've etched it first with 1% amyl nitol, and then followed that with 4% pickerel. And you can see the microstructure nicely. On the right, I etched only with nitol, and then I did the Pepperhoff deposition process, where you vacuum deposit a compound with a high dielectric coefficient. In this case, it's zinc selenide, and that colors the structure. And you can see the surface, the interface layer, much better because we have higher magnification in the vertical direction there. And the second phases are all colored. Now, when I did this, you cannot electroless nickel plate a zinc aluminum coating like this. So I electrolytically deposited some copper on the surface, and then I electroless nickel plated above the copper for edge retention purposes. But you can only see a tiny bit of the copper coating there. And this is electro-galvanized zinc nickel, and you can see a lot of cracks in that microstructure. And it's etched with the 1% amyl nitol or 1000X. And here is a transmission electron microscope shot, a thin foil of a vapor deposited layer of stainless steel that was removed from a piece of sheet steel. And you can see the grain structure very nicely. And there's no annealing to it. Well, I see at least one annealing to it in there, but not much. Now let's look at some Babbitt metal on steel. And this is often used for applications involving wear. And this is a tin 9% antimony, 5.5% copper Babbitt metal coating. On the left, you can see it's been etched with nitrile. And it's etching both the coating as well as the sheet steel. On the right, it's just as polished. And you can see just by reflectivity differences, some aspect of the second phase is in the Babbitt metal coating. And the substrate was 1010 carbon steel. And here's another example. This is tin 9 antimony 5.5 copper. Same samples before, but now it's color etched with Clems number 1, which is coloring the ferrite grains beautifully. And we're only at 50x, so the grains are small, but you can actually see on the top surface some of that second phase quite clearly. And this is copper 30% lead Babbitt metal coating on a steel substrate. It's formed centrifugal casting. And you can see this has been etched with nitrile, and you can see structure in the Babbitt metal coating the copper 30% lead. And also, of course, you can see the microstructure of the steel, and that's at 50x. And it looks like there's a couple cracks in there. And let's look at a little chrome-plated steel. Now, chrome plating is a really weird product because it's the only coating or anything that I know of in a metal where it's necessary to have some internal cracks. General Motors actually has charts with preferred crack patterns versus rejectable crack patterns in the chrome plating. Apparently, it's very brittle. And if you get some fine cracks in there, it relieves the brittleness so that it works in service. Now, I took this picture. Oh, the substrate here is Maraging steel, 18 nickel 300, which is a pretty high strength version of Maraging steel. There's 18 nickel 200, 250, 300, and 350. The most commonly sold is 18 nickel 250. And the 200, 250, 300, 350 refers to the tensile strength and KSI. And the 18 nickel 350 is only used in nuclear weapons. You can see two vertical cracks there. I photographed this a number of years ago using Polaroid film. And you see where the two arrows are? Well, there's a horizontal crack there, but no matter what I did with the Polaroid film, I couldn't see the crack. And unfortunately, I didn't have any ordinary Kodak photographic film, or I'm sure I could have captured that crack. This microstructure is etched with a modification of Fry's reagent. And it's a very low Lath-Martensite because those Maraging grades have less than 0.03 weight % carbon in them. And this is chrome-plated 300M steel in the as-polished condition on the left, and you can see those two cracks. On the right, it's etched with nitrile. And the vertical cracks we can photograph, but I can't photograph on Polaroid anyway. I couldn't capture the horizontal crack. And this is chrome-plated 4340 alloy steel, and Brightfield on the left, Nomarsky on the right. This is as polished, and you can see cracks in the chrome plating, which are perfectly fine. Each picture's at 200x. Let's look at a couple of thermal spray-coated, plasma spray-coated sheet samples. This is the same specimen. Now, according to ASTM standards on preparation of thermal spray or plasma spray coating, you should never hot mount your sample because the compression is going to make the coating look more dense than it really is. They tell you to only use cast epoxies. And one of the techniques that's been widely used is to add some fluorescent dye to the epoxy. and then use a detector with your light microscope that can see the fluorescence. And you can then tell where the epoxy has gone into these cracks because they light up green. But these weren't, on the lower left of the picture, that was vacuum impregnated with epoxy. And those are the true cracks. You get these horizontal cracks, those are splat cracks, linear cracks. And in the upper right, you hardly see any of those cracks. But they're in the lower left, that's the real structure. And the surface is much more rough with the proper mounting, the vacuum impregnated epoxy, compared to the thermosetting resin in the upper right. And I know there are several companies in the United States that insist on mounting their sample in the hot mounting press. Why? Because they say it looks better. But they're deliberately looking at an untrue structure. And they're violating the ASTM standard. And we've had arguments with these people several times over the years, over the last 20 years, but they still insist on doing it the wrong way. Here's another example of, this is plasma spray coated chrome nickel on a steel sample. And you can see along the interface between the steel and the coating, those are particles from shot blasting the surface. For years, I kept saying to these people, you know, why don't you, after shot blasting, wire brush the surface to dislodge those embedded particles? Because you got now hard, brittle particles at the interface. This is not good. Well, finally, I've been told that the industry is recommending that people, when they make the thermal spray or plasma spray coated sheet steel samples, that they wire brush the surface first before they do the coating, because they've actually had some defects start at those hard, brittle particles at the interface. But at least that's a true structure.